into vector notation. This thing just is nothing else than the transpose of that vector and then taking complex conjugate. Moreover, when you see something like this, then it's an inner product, means it's just a product of these two vectors. And actually that's also the reason why this notation is useful, is because when you have more complicated formulas to work with, you can actually quickly see that these are numbers, and often these numbers are 0 or 1, and you can just ignore those terms. But so we had the notion the notion of a qubit, which was a superposition, a possible superposition of the 0 state and the 1 state, and you had the property that if you square these amplitudes and sum them up, then you get equal to 1, and when you measure these qubits, then you will see 0 with probability alpha squared and 1 with probability beta squared. Moreover, if we went to more than 1 qubits, like n qubits, you can have in all generality, you can have a superposition over all possible basis states, all possible 2 to the n basis states, each with a particular amplitude, and the property should hold that the amplitude squared sum up to 1, and the probability of observing the jth state is equal to alpha j squared. Another thing that I showed yesterday, and if you were a good pupil, you actually did the homework exercise. There's probably nobody who did it. It says that if you have a n-bit basis, so a basis state consisting out of n bits, y1 up to yn, and you apply the n-fold or the tensor of n-fold Hadamard transform to that state, meaning that you apply the Hadamard to y1, Hadamard to y2, etc., then you get this sum, which is an equally weighted superposition over all basis state, but there is this phase, so these things are called phases, in front of there, and positive or negative, they can be complex too, of -1 to the x dot y, where x dot y is the inner product. You might also recognize that this is a Fourier transform. Moreover, if you just have all zeros and you apply this Hadamard, then you get an equally weighted superposition, and all the phases will be +1. Okay. So now let me switch to computation. So how can we actually do? How can I demonstrate that it is useful to have quantum algorithm, as I sketched yesterday, using qubits, a measurement, a unitary followed by a measurement, where the unitary, if you want it to be efficient, is computable by few, polynomially many, of this universal set of gates. So, because it's so hard to prove anything about classical normal computation, I switched to a simpler model called the black box model, or decision trees. And in all generality, I mean, Sasha has been talking about this, think of it as having n variables called the inputs, and I want to compute some Boolean function f of these n inputs, and as complexity measure, I don't look at the size of the circuit, but I just look at how many of the variables x1 up to xn do you read, do you look at. So this is a very simple model, which has the good property that it allows you to prove to prove that the complexity in this term of specific functions, you can exactly determine it. You can prove tight upper and lower bounds. So it's a good test case to work with your model. So let's look at the very simple problem, and let's look at the parity of computing the parity of x0 and x1. Now, classically, if you want to know this perfectly, if you want to compute the parity of x0 and x1, you will need to look both at x0 and x1. If you just look at one of the two, then of course you still don't know the parity, because you don't know the other variable. However, if you were allowed to use quantum mechanics and quantum algorithms, and this is the first algorithm I will discuss, you can actually do that with just one query. Okay. So I have to explain what a quantum query is, because I haven't told you yet. And the idea, of course, is that classically you can query x0 or x1. Quantum mechanically, you should be allowed to query both x0 and x1 in superposition, because that's what it's all about. So in particular, querying x0, I model in the following way. You enter sort of the state 0, indicating that you want to query variable 0, and you get back -1 to the power x0. So if x0 is 0, then nothing changes, but if 0 is 1, then you get a -1 in front of your state. Now on basis states that of course is not possible to see, but bear with me. If you query x1, then of course similarly you get a -1 in front of your state if x1 is 1. And by the way, I have to do something different than normally, because my query has to be a unitary operation. Particularly, it has to be reversible. So I have to make it fit the framework, so to speak. Now, in general, I can have a superposition of the query 0 and query 1, where alpha and beta, of course, have to sum up squared to 1. And then the answer that I get back after doing this single superposition of superposition query is a -1 because of linearity, a -1 to the x0, this should be a 0, plus a -1 to the x1, 1. So I get both answers in superposition. Sorry about this, this should be a 0. Okay, is that clear?
And this is the unitary operator for every fixed x0 and x1,
yes.
Right?
So, but how you get the input? So initially we have, if you want to compute classical parity function, so we have a classical input string of 2 bits.
2 bits.
And we represent it as a state of 2 qubits of a single state. Not mixed state, but primitive state when one bit is in state 0 and the other is in state.
Yeah, but sort of think of it as oracle. I think of it as oracle. So you have these 2 bits, 0 and x0 and x1, but you don't know what they are, what the values are, and you now want to determine the parity of these two by making queries to these variables.
Yeah.
And this is what it means to make a query. If you want to query 0, then you enter 0 and you get back -1 to the x0. 0.
So, but what we get, what we have as an answer for the query, it's just.
This is the answer for the query.
So it's a state of which system?
So you as you prepare
with 2 bits.
For example, look at it here. You prepare this query, which is alpha 0 plus beta 1.
Mm-hmm.
And now you enter the query, so you enter the query mode of your algorithm, and then you push a button, and then the query is answered, and then you are in this state, the state after the error.
Mm-hmm.
The state of query device changes after query, and this is the rule of the change.
But so the mystical query device has 1 quantum bit inside, and there are 2 classical bits.
Yes.
Which influence in a mystical way the states after the query.
It's not mystical. All this is how it's done.
Yeah, but it's no specific physical picture. What is the query? What we send them? How we
It has nothing to
represent.
do with quantum measurement, so it's just unitary.
Yeah, you can.
okay.
The point is that you
It's not measuring this qubit. It's just
it could be that the value x0 and x1 themselves are algorithms that compute it, and they will be then it's nothing mystical. Then there's just this algorithm that will be run, and we'll put this space in front of the state.
Yeah. Okay.
Okay. Maybe it will become clearer along the way, but It may look a little bit mystical, but it's not really. Okay, so if these are the rules of the game, then let me show you how you can do this with just one query. And this, by the way, was Deutsch's original algorithm, or first algorithm, which actually wasn't quite like this, but still I would like to attribute this to him. So what he does is the following. He starts with a 0, classical 0, and applies Hadamard to it. No query yet. So as we've seen yesterday and from the previous slide, you get this superposition of 0 and 1. Right, that's what the Hadamard does to the 0. Then he makes the query, and the only query that he will make, resulting in this state. Right? The 0 will get a -1 to the x0, and the 1 will get a -1 to the x1 in front of it. So this is the state that you get back after making your first and only query. Okay. Then the recipe is as follows. You apply another Hadamard transform to the state you have so far. So let's do that. And note that if I apply a Hadamard to this state, then because of linearity I can compute it by applying a Hadamard to the first part and a Hadamard to the second part. It's a linear combination, so applying a Hadamard to this first part will give me a 1 over, multiply with 1 over square root of 2, so I get 1/2. This thing remains the same, but the 0 changes now into 0 plus 1, because that's what the Hadamard to the 0 does. And again, by linearity now I apply a Hadamard to this part, which will give me again a -1 to the x1, but now this 1 will change in 0 minus 1. Right? Because we saw yesterday that the Hadamard of 1 will give you a 0 minus 1. So applying a Hadamard to this whole thing is equivalent, I mean, will result in obtaining this particular state. Okay? So I copied it. So here it is, that state. And now I'm going to rearrange the terms in there, and then you will see why this was a good thing to do. So I'm taking the zeros from this state, and I'm grouping them together. Right? The 0 here has a -1 to the x0, and here it has a -1 to the x1. So in front of the 0 state I have -1 to the x0 plus -1 to the x1. And if I take the ones and I group them together, I get -1 to the x0 minus -1 to the x1, and that's because there's a -1 here. Nothing special, I just rearranged the terms. So now look at this thing, and imagine that the parity of our two variables, x0 and x1, was 0. This could come about because either x0 was 0 and x1 was 0, or x0 was 1 and x1 was 1. Both were the same. So in this situation, let's just assume that it was the case x0 is 0 and x1 is 0. The other case is exactly the same. And now look at this state I have here. And let's look at this top part. So x0 is 0, so that means that here I have -1 to the 0, that's 1. And here I have -1 to the 0, which is also 1, so here I have 2. Multiplied by half is 1. So that means the amplitude sitting in front of the 0 basis state is 1. That means that if I measure this thing, then the probability of seeing a 0 is 1 squared, is 1. And we could verify that actually the probability sitting in front of the 1 has to be 0. Because here I have -1 to the 0 is 1, and here I have -1 to the 0 is 1, but I subtract these things here, so there's 0 indeed in front of the 1. So if I observe this state, if I measure this state, I will always measure 0. Okay? Now, if we only 0. Now, if we change the setting and assume that the parity was 1, then again, let's assume that we are in the case where the first variable is 0, the second variable is 1. Then we'll see that this term is -1 to the 0, which is 1, and this term will be -1 to the power 1, which is -1, but because there's a minus here, it becomes +1, and now this term becomes 2. And hence, multiplied by a half, the probability of observing the 1 now becomes 1. Okay? So, to cut the story short, if you measure this state and if the parity of the two variables was 0, then you will always observe a 0, and if the parity of the two variables is 1, you will always observe a 1. Hence the algorithm works. It will tell me exactly the parity of these two variables. Okay, so, and actually I'm doing this so slowly because, first of all, it's nice because you can see the sort of the interference and the stuff going on. And second is because this is like a general framework for many algorithms, including Shor's factoring algorithm. So let me go up one step and make it a little bit more interesting and extend this idea to constant or balanced, which is now called the Deutsch-Josa problem. So this we did shortly afterwards with Richard Josa, and now it's a promise problem, and it works on n variables, and it says that I promise you, I give you n variables, and I promise you that either all the variables have the same value, they're either all 1 or all 0, or I promise you that half the variables are 0 and the other half is 1. Okay? And your task is to determine which of the two it is. Now classically, it's easy to see that if you want to not make an error, then you have to ask half of the variables plus 1. Now it's clear that if you ask only half of the variables or less, then you still cannot be sure if they were answered all the same value, whether the other half that you have not seen are the opposite value or the same of you. But as soon as you have seen half plus 1, then you know that either you have seen all the same, and then you know because of the promise that everything is the same, or you have encountered two different values, and you know that you are in the balance case. So classically, n over 2 plus 1 is needed, and it can be done also. Quantumly, it's still just one query. Without making an error quantumly, you can still do this in one go. And you have seen the algorithm because it's basically the same. Note now that querying state I, querying variable I, will give me a -1 to the xi in front of basis state I. And I can have an arbitrary superposition of variables that I want to query. And then the answer I get is this arbitrary superposition back, but a -1 to the xi in front of state I. Okay? It's just a logical generalization. Okay, so here's the Deutsch-Josa algorithm, and you should see the resemblance with Deutsch's algorithm. We start out with not just the 1 0, but with n zeros, and we apply the n tensorfold Hadamard to this state, resulting in an equally weighted superposition of all the basis states. Again, those who did their homework agree. And now, second step of the algorithm is to do a query. Just like Deutsch, do one single query, which will result in this state, but in front of the basis state I get phase -1 to the xi, just in one swift go. And now the third and last step is to apply the Hadamard again to this state. And you have to use this other rule, Hadamard to an arbitrary state, and do linearity, but if you do it correctly, you will get a double sum, where you will get a superposition over all j, and for each of these j's you have to sum over all i's, and you get -1 to the xi plus the inner product of I dot j. And this is the thing that comes out if you do it. It's nothing hard. So this is the state that you have in your hands after making your only query. So I copied it. Here we have the state with this double sum. And now, because I want to get rid of the double sum, let's zoom in on those basis states where j is all zeros. So let's take out of this sum only the terms where this is all zero state. And when I do that, I can compute the amplitude that is sitting on this all zero state. And by squaring that, I get the probability of observing the all zero state. So taking out this all zero state, I get this sum, I get 1 over 2 to the n, and then I have minus 1 to the xi. Because j is all 0, the inner product of I dot j is all 0, so this part vanishes, and the only thing that remains is xi. Okay, so this is the amplitude, well, this sum is the amplitude that sits on the all 0 state. Now, look, if I was in the constant case, and all these xi's were, say, 0, then this sum, all these terms minus 1 to the 0, would be 1. And since there are exponentially many, this sum would sum up to 2 to the n, but since I have to multiply with this 1 over 2 to the n in front of it, this sum then sums up to 1 perfectly. Meaning that in the constant case, I will observe 0 to the n with probability 1. On the other hand, if we are in the balanced case, then half of these terms are 0 and the other half is 1, and they all neatly cancel, and that probability is going to be 0. Right. So either I observe the 0 and I'm sure that we were in the constant case, or I observe another basis state, anything but the all zeros, and I'm sure that I was in the balanced case. Okay, so again, yeah, question?
When you say classical, you mean deterministic or randomized?
I mean deterministic. I said that you want to be certain that the answer is constant or balanced. And you're absolutely right. If I allow myself randomness, then I can also do it with a constant number of queries.
But not 1.
Well, then with probability half.
No,
1 is not enough. 2 is not enough either.
No.
2 is better. Yeah, 2 is better.
2 is good, but 1 is good too, because with probability half you will say
Probably half it is 0 first.
No, but you have the property that in one case you will not make an error. So I guess in the case when when you're constant, you will always say constant, and in the case where you're balanced, you will say balanced with probability half. So with one randomized query, I'll come to that a little bit later, but bear with me that we're deterministic, classical, and I would say deterministically quantum, right, because there's no error. Okay. Actually, this is not good because let me switch to my lecture of yesterday, because actually see? Okay, so I've shown to you now the Deutsch and the Deutsch-Jozsa algorithm, and I will not have time to go in detail to these others, but I want to tell you that after, just for historical perspective, after the Deutsch-Jozsa algorithm, there was an algorithm due to then Simon, which actually precisely touched upon this point that Edward just pointed out, that this Deutsch-Jozsa algorithm is not really good algorithm or a good problem to separate quantum from probabilistic algorithms. And Simon has a problem that still is easy quantum mechanically, so requires few queries, but requires many queries still, even in the probabilistic setting. And this is also interesting because Shor's factoring algorithm came out of Simon's algorithm itself. And there's this anecdote that I think Shor was in the program committee of Stock or something, and he really liked Simon's paper, but the committee didn't like it, so they rejected it, and then Shor got to think about it, and he actually saw how to use these ideas and push them to do the factoring algorithm, and on the way he was sending emails back and forth to then Simon, but then Simon didn't really understand what Shor was talking about, and then in the end Shor had come up with this algorithm by his own.
But the paper was too rejected.
Sorry?
The paper was too rejected.
The paper was, well, that was later, so the paper was rejected, and then I think it was accepted the next Stock or Fox, because of that, but then it became apparent that it was really important because it led to this factoring algorithm. So this is how these things go. So a little bit about the factoring algorithm. I didn't want to explain that in detail, although that's not hard, but I would need a whole lecture for that, and I want to say other things also. If you all know, factoring is this hard thing. Classically, we have no fast algorithms. For example, if I have a 300-digit number, then it still requires more than 100 years of current technology. However, if I had a quantum computer that would run in a reasonable clock speed, then you can solve these numbers in a minute.
But if you have the time of building the quantum computer?
Well, we're working on that, so maybe 10 years.
And what size you need?
It's only equals.
And also this 100 is grossly underestimated.
What size would you need? I mean, how many qubits will you need?
Good question. I once calculated it, and I think if you want to add all the error correction and the fault tolerance stuff, you need at least 10,000 qubits to factor 300 digits. I mean, 300 digits already becomes like 1,000 qubits just to represent it, and then you need some overhead, etc.
So it seems like it's quadratic.
What is good at here this thing?
No.
Actually, this is actually.
I mean the number of qubits. Is it quadratic in the number of digits to factor?
No, that I don't know. Wow,
You said you calculated.
Thought about it. Yeah, well, I calculated it for this particular case, and I'm not sure the growth rate is quadratic. Probably not. Actually, I don't think so. Okay, and I have to advertise this, but of course this is very bad for cryptography, because it will break all modern, or most of modern cryptography, like RSA, etc. And so if you build a quantum computer, you destroy this. Nevertheless, this is a reason to put lots of money into quantum computing. Actually, I don't quite understand that point. Still, somehow this seemed to have triggered people to say this is good, and not scientifically it's interesting, but also other agencies and whatever suddenly think it's very interesting. Of course, RSA is very interested. NSA is very interested in this. Anyhow, very shortly, Shor's algorithm. The following: suppose that you want to factor a number n, then the first step of the algorithm is to classically show, and this was known, that you can reduce this to the following problem: given a number x, find the smallest r such that x to the r mod n is 1. So if you could solve this particular thing for general x and n efficiently, then you can factor. This is 3 lines of algebra, it's easy. And what Shor then did is he devised a fast quantum algorithm for this period finding problem. And then there's actually more to it, because there's still some classical post-processing, because it doesn't exactly give you the period, but something from which you can deduce what the period is. So there's some classical post-processing to actually indeed get a factor of n if it exists. Okay, so that's sort of in a nutshell Shor's algorithm, and the basic trick, or the basic thing of the quantum part, is that instead of doing this Hadamard transform, which you can view as a Fourier transform over Z2, you now want to compute, or Z2 to the n, you want to compute a Fourier transform over Z2 to the m. which is this following thing. If you have a basis state 1 up to m, you go to this exponential sum. There should be how do you say this? A constant in front of here to make it 1. But instead of -1 and +1, you have all complex phases, all roots of unity there. And moreover, Shor was lucky because he showed that the Fourier transform can actually be efficiently implemented. So with few Hadamars, these rotations and C-naughts, you can implement this Fourier transform quickly. Won't have time to show you all this, but what I can show you is that this is again the scheme of this period finding algorithm, and I'm just showing this because it resembles so much the Deutsch-Jose algorithm. It has these 3 steps. The first step is the preparation, where you start out with zeros, you apply your Fourier transform, and you get this superposition. You could even take Hadamar in this first step. Then the second step is doing a query, which in this case is not a query, but it's computing x to the j mod n. So I guess sort of this is where, instead of a black box thing, you have an algorithm which computes this value for you. And then you apply your Fourier transform again, and you look at this state. No need to look at the calculations, but from this state, if you measure it, you can deduce what this period was. You shouldn't understand this, but I'm putting this because it's the same. It's the same thing as the original algorithm. Okay, and fourth algorithm that draw a lot of attention. I mean, Shor's algorithm is kind of not very useful, because who on earth is interested in factoring numbers, except if you want to break the rules, but nobody really wants to break the rules. I mean, I'm in Russia, so that doesn't work. No, but seriously, who wants to factor? I mean, I never had the urge of factoring a large number. However, there is a much more useful algorithm, that's Grover's algorithm. However, it has not an spectacular speed up as Shor has. And it shows the following. So does the following: suppose you have n variables and you want to compute the OR of these n variables, or you want to know that there is a variable that's 1, then classically randomized even, you still need a constant times n number of queries to determine whether there is a variable that's 1. However, quantum mechanically, Grover came up with an algorithm that only uses square root of n queries. So there is a square speed up in this particular case. Okay, so that's all I want to say for now about quantum algorithms, and I want to sort of apply these into other areas. And in particular, I want to introduce Alice and Bob. There's Alice and there's Bob. And of course, when they are quantum mechanically, they have all kinds of trouble that they have normally, but in addition, they have even more problems. I guess this would be also a good one to use at home. How can you be sure I wasn't there? Well, so in particular, since we have seen these nice things that you can do with quantum algorithms, what happens when we use them for communication? In particular, what happens when we want to communicate a message from Alice to Bob, and Alice and Bob are not using bits, but they're using qubits? How much does that help? And it turns out that one of your countrymen, already in '73, how do you pronounce, how is it Kolevo? Because you don't have H. Kolevo. Okay. Showed that if you have...
I was working yesterday.
He's here now. Okay.
Exactly.
Okay, I met him a couple of times.
How old is he now?
Yeah. In '73, he showed that if you have a message, well, putting it in my language, if you have a message that contains k, is built out of k classical bits, then you cannot compress this message into k-1 qubits. Or put differently, the information that you can put in a single qubit is not more than one single bit. Okay? So that's a bit of a disappointment. Nevertheless, it's true. So I want to switch gears once more and go to a somewhat more interesting setting called communication complexity, where now Alice and Bob are not interested per se in sending a message to each other, but they're interested in computing some Boolean function that depends on both Alice's inputs and Bob's inputs. So Alice has n bits and Bob has n bits, and the game is that Alice and Bob can send back and forth messages, classical bits, and then at the end of the day Alice has to know the value of the function f, x, y. And of course the goal is to minimize the number of bits that they send back and forth. Otherwise it's not interesting, because Bob could just send this string y to Alice and then Alice can compute it. And of course we are interested in whether you can do better, and if so, how you can do better. For example, the first problem that comes to mind is this equality problem, where Alice and Bob want to know whether the two inputs they have are the same or not. And it's fairly easy to show that you need n bits, and I already showed to you that you can certainly do it in n bits. If again we want to be deterministic, we don't want to make an error.
But quantum algorithms are necessarily randomized, that is, they necessarily will have some errors.
No.
I mean physically.
Look at my Deutsch-Josa algorithm and the Deutsch algorithm. There were no errors there.
Yes, but you wouldn't be able to simulate this in a real quantum machine.
Well, I don't have one. So.
it must error with some probability.
But the error then comes from the fact that my device that I didn't really perfectly implement it to Hadamard.
Yes.
But it didn't come from the algorithm itself.
Okay, but the result will be more or less the same. You have error.
No, but I can control the error by making if I implement my device better, then the error will be smaller. And still I make only one clear. But you're absolutely right that of course the interesting model to investigate is when you have error. But it is important that this is a difference, right? The error coming from your hardware or from the software. Okay, so equality when you want to compute it. And you might say the same thing about these machines, right? They have error too. But nevertheless we want to have algorithms